You know, probability is really just a guess of the future based on the information that we have at that time. But if we get more information at the very last minute, think about it, there should be a way that we can incorporate that information to make our guess a more accurate guess. And that's what we're going to cover today, conditional probability. Let's try and remember the important stuff we did last time, because that's going to be incorporated here as well. Here's an example. We have 4 boys and 2 girls randomly seated, and they're seated in a row. Let's first of all consider the sample space. How many ways can we seat these 4 boys and 2 girls? Well, it's going to be a factorial, isn't it? The first seat has a choice of 6 people. Second choice has a choice of 5 people, on down to the last person who won't have a choice. Okay, so if we multiply that out, our sample space, or I shouldn't say our sample space, but the number of events in our sample space is 720. Now we want to know the probability that, you ready for this?
No, I can't take it. I can't take it, Jerry. It's too much. It's too much.
This is a good review. We want to know the probability that a boy is seated at the left end or a girl is seated at the right end. Well, what's the trick with ors? Do you remember? Well, what we do is take each probability individually and use the addition property of probabilities. Let's for instance first get the probability that a boy is seated at the left end. Well, we have our sample space, so let's find out how many ways a boy can be seated at the left end. Well, that's going to put the first seat at the left there has a choice of 4 boys, and then I fill in the other seats based on anybody else, 5, 4, 3, 2, 1. And if I multiply that out and put it over my sample space, I get 480 over 720. Okay, it can be done. I'm not going to worry about doing the calculation. Now we take the probability of the other event, a girl being seated at the right end. Well, we only have 2 girls, so we'll start with that girl at the right end with the 2, and then fill in the other people, 5, 4, 3, 2, 1. That comes out, I hope you see, to a different number over the sample space. In this case, it's going to be 240 over 720. Now I've got both of those, and then I get the intersection of the 2 events. Both events happening at the same time. A boy seated at the left end and a girl seated at the right end. Well, that gives me a choice of 4 boys at the left and 2 girls at the right, and that only leaves me 4 more people in the middle. So then I have the 4 on the left, the 2 on the right, and then I fill in 4, 3, 2, 1 in the middle. And if you multiply that out, it comes out to 192 over 720 over my sample space. Now why did I do that? I can get my OR by using the addition formula of probabilities, and that is to add the 2 probabilities of the separate events and subtract out the intersection of the 2. In this case, 480 plus 240 minus 192 over the sample space.
With all due respect, sir, I believe this is going to be our finest hour.
So we can use this addition formula, and you will use it anytime you have an OR. Be very useful. Then there was the complement theorem. Do you remember the complement theorem and what we knew about a full sample space? If that was set A, its complement, everything but A, the probability of any event, in this case A, is going to be 1 minus the complement of the event, because all the probabilities in an event add up to 1. Remember?
I know that, dude.
Well, everybody seems to know it, but nobody seems to want to use it. Let's give an example. Okay, we have 5 cards dealt from a standard 52 card deck, and I want to know the probability that at least one card is a spade. At least one card is a spade. Well, if you think about it, we're going to have to know then the probability that there's one spade, the probability that there's two spades, the probability that there's three spades, four spades, all the way. I have to figure out 5 separate probabilities in this case. For instance, and we'll just do it the hard way for a second here, the probability that there's one spade out of the 5 cards dealt. Well, let's see. I generate that first spade with a combination of 13 spades. There's only 13 spades in the 52 card deck, taken one at a time. And then the other 4 cards have to not be spades. So how many cards in the 52 card deck are not spades? 52 minus 13, or 39, taken 4 at a time. And I put that over the sample space, a combination of all 52 cards taken 5 at a time. So that's going to be what I'm going to have to do to produce the probability of one spade, exactly one spade. Now let's add the probability of 2 spades. Well, let me produce that 2 spades, which is a combination of 13 spades taken 2 at a time, and then I have the other 3 cards, and that'll be the other 39 cards that are non-spades taken 3 at a time, over my sample space, combination of same sample space, 52 cards taken 5 at a time. This is getting difficult, and I can continue on and do each one of those and have to put it in the calculator. What a nightmare. Or, remember, I'm trying to find out at least one card is a spade. How about subtract from 1 the probability that there aren't any spades?
But that's so easy. I should have thought of it for you.
Well, that's what we got to get you to think about all the time. Often, it's much easier to figure out the probability that something isn't going to happen and subtract it from 1 than it is to find out the probability that it is going to happen.
No problemo.
Okay? May not be hugely easy, but it's easier. Okay?
You'll come again.
Let's do one more for review, and then we'll begin our new stuff. We have 5 cards dealt from the 52 card deck. We want to know the probability that all the cards are hearts or all the cards are spades. Now this is an interesting situation because it's going to involve 2 things that are, what we said last time, mutually exclusive, things that can't happen simultaneously. So we can use the addition theorem of probability, but we don't have to subtract, well, you can, you don't have to subtract the intersection because the intersection is 0. They can't happen at the same time. So we'll have the probability that all the cards are hearts. Let's see, how many ways can that happen? A combination of the 13 hearts taken 5 at a time for this hand over your typical 5-card hand combination. Let's see, over your sample space, 52 cards taken 5 at a time. So there's your probability that your 5 cards are going to have all hearts. And we can add in that they have all spades. That's going to be 13 spades taken 5 at a time over 52 cards taken 5 at a time. Now if you think about it, we could have just multiplied by 2, I guess. But anyway, the point is, in this case, we're not going to have to subtract out the intersection because there is no intersection. Okay, now let's talk about our new stuff today, conditional probability. With conditional probability, we have some added, possibly recently added, information we want to incorporate. The definition of conditional probability, and this is the way it's read: the probability of A given that B has already occurred. There's your new information. The probability of A given that B has already occurred. Well, you might say, well, what does that mean? Well, how's that going to change anything, the fact that some other thing occurred? Well, let's consider this. Consider we roll 1 dice. Let's try and make this simple, at least to begin with. Our sample space, of course, with one dice is 1, 2, 3, 4, 5, or 6. That's the only possible things you can roll, right? The number of outcomes in that sample space is 6 outcomes. Okay? So the probability of getting a 5 is the number of ways of getting a 5 over the sample space. So how many ways can I get a 5? Only one. So the probability of getting a 5, quite simply, is 1 out of 6. I think you already knew that.
Wait a minute.
What if I said I want the probability of 5 given that an odd number has already been rolled? Now, I have some new information. The new information is that an odd number has been rolled. Well, the number of ways I can get a 5 hasn't changed, has it? There's only one way to roll a 5. But my sample space has changed, hasn't it? The number of possible ways that I can get an odd number has changed. I've reduced that sample space from 6 items to only 3. Haven't I? 1, 3, and 5. So, that changes everything. The odds of getting a 5, given that an odd number has already been rolled, is not 1 out of 6, but rather 1 out of 3, or 1/3. Let me show you the actual formula for the conditional probability. Well, normally, the probability of A and B both happening, we'll say the intersection of A and B, would be the ratio of A and B both happening, the intersection, over our complete universe. Every possible thing that can happen. Okay? But now we know we can limit what happened. With conditional probability, the probability of A intersection B is still going to have the same numerator. Okay, that intersection is still going to be in the top, but we know that B happened. So you see, our sample size is significantly reduced, all the way from the universe all the way down to just B. I hope you can see that. Okay? Consequently, the formula that we'll use for conditional probability, as long as we're positive that B has already happened, is going to be the probability of A intersection B, not over the sample space anymore, but rather over the probability of B occurring. Let me try one. We have 2 dice rolled this time. Now the sample space for 2 dice normally would be 6 for the first dice and 6 for the second dice. I'm going to differentiate them as red and blue. Will be the number of things that occur in the sample space is 36, isn't it? Let's consider what the probability that a 12 has been rolled. Okay, well, I think you already know that. So there's one way to get a 12, and there's 36 in the sample space, but it's 1 out of 36. What's the probability that a 12 has been rolled, given that at least a 10 has been rolled? Well, now we've got a condition, a conditional probability. We're going to use the probability of A intersected with B over the probability of B. A is that a 12 has been rolled. B is that at least a 10 has been rolled. Well, let's think about this. The probability that a 12 has been rolled is 1 out of 36. What is the probability that a 12 has been rolled and at least a 10 has been rolled? Well, that's what it is. That both of them happened at the same time. It's still 1 out of 36. That's not going to change, remember. It's our sample space that's going to change. What is the probability that at least a 10 has been rolled? How many ways can we have at least a 10? I'm thinking there's 6 ways to get at least a 10. 1 way to get a 12, 6 and 6. 2 ways to get an 11, 5 and 6 and 6 and 5. That makes 3. And then 3 more ways to get a 10, 5 and 5, 6 and 4, or 4 and 6. So there's a total of 6 ways. So our probability of getting at least a 10 is 6 out of 36. So using this formula, our probability of getting that a 12 has been rolled, given that at least a 10 has been rolled, let's reduce it, is going to be quite higher, 1 out of 6. Okay, let's do another one. What's the probability that the red die shows a 5, given that a 10 has been rolled by one of the two? I don't know which one. I'm sorry. A 10 has been rolled total. Okay, that the red die shows a 5. Well, how many ways, or what's the probability that both happened at the same time? A red die shows a 5, and at the same time, a total of 10 has been rolled. Well, there's only one way for that to happen, isn't there? One way, a 5 and a 5, okay, to get the 10 and to have a 5 showing on the red die. Okay, what is the probability that a 10 has been rolled, period? How many ways is there to get a 10? Well, there's 3 ways to get a 10. 5 and 5, 4 and 6, and 6 and 4. So the probability of getting a 10 is 3 out of 36. So the conditional probability that the red die shows a 5, given that a 10 has been rolled, if we reduce, is going to be 1 out of 3. That's the way we do conditional probability. Let's try another one. We're going to take a survey of state spending, and it reported that 15% of the families bought a new home. 21% of them bought a new car, and 8% bought both a new home and a new car. That smells of intersection, doesn't it? Now on the surface, this one might look like it's going to give you a headache, but I'm thinking since they gave us the probabilities of everything, all this is going to be a drill in is putting the right thing on top in these probabilities, okay? Let's figure out what the probability that a family purchased a new car given that they purchased a new home. Okay, remember, this is conditional probability. We'll go through it. It's going to be the probability of both things happening at the same time over the probability of B. Okay, let's see. The probability of A intersected with B, in other words, that they bought a new car and a new home, they gave it to us. How many bought both a new car and a new home? Was 8%. 8% bought both a new home and a new car. So there's your numerator. Okay, your denominator is the probability that they bought B, the probability that they bought a new home, and that they gave us 2. 15%. So 8% over 15%. I'll reduce the percents by multiplying by 100 basically.
Next.
And I've got 8/15. Okay? Let's do another one. The whole idea here is to get in your mind the idea of conditional probability and the formula that you use. What's the probability that a family purchased a new car or that they purchased a new home? Well, wait a minute. We've got an or here. We've got an old trick we're going to use with ors. Remember? The probability of A or B, or I say probability of A union B, is equal to the probability of A plus the probability of B minus their intersection probability. And well, we have all those numbers too, don't we? Okay, let's look back at the problem. The probability of A union B is going to be the probability of A. Let's see, that's going to be the probability that they purchased a new car. That's 21%. Plus the probability of B, that's that they purchased a new home. That's 15%. Minus the intersection, that's that both happened at the same time. That's 8%. Once again, 21% plus 15% minus 8%. Now, we knew that we were going to use that formula because we smelled that or, didn't we? And that comes to 28%. That's the probability that they did one or the other. We're going to use that number to answer this question. What is the probability that a family purchased exactly one? What I mean, either just the house or just the car, given that they purchased at least one of the two. Okay, this is a definitely a conditional probability problem. Well, we're going to have to figure out on the numerator the chance that they purchased exactly one. Well, we'll have to add the two, exactly one house and exactly one car. We can figure out those probabilities from the numbers they gave us. The probability that they figured out that they purchased exactly just a house is going to be 15 minus 8. Now, why do I say 15 minus 8? Well, 15% of them bought a new home. 8% of them bought both. So if I subtract 15 minus 8, I'll get the ones that bought a new home but didn't buy both. In other words, they only bought a new home. So I'll add that to 21 minus 8. Now, why 21 minus 8? Well, 21% of them bought a new car. 8% of them bought both. So if I want the ones that only bought a new car, it would be 21 minus 8. And we'll put that over the number we just figured out of the people that bought either a new car or a new home. We just figured that one out in the last problem. We do a little simplification. 15 minus 8, 7, plus 21 minus 8, 13. So 7 plus 13 is 20 over 28.
Oh, yes.
There's a 5/7 chance, 5 out of 7 chance that they purchased exactly one, given that they purchased at least one of the two. That was a tough one. But remember, the formula for conditional probability is going to be the probability of A given that B occurred is going to be the probability of A intersected with B over the probability of B happening alone.
Thank you, sir. May I have another?
Okay, let's see. Let's do this one. It's always useful to be able to come up with some interesting statements based on a perhaps arguably boring table here. Okay? Well, what we have here is a table that summarizes a survey taken of 100 people. The whole thing adds up to 100. Regarding canceling spring break. Some people are for it and some people are against it. As you can see, we've divided it by party as to who's for and who's against it, and some people have no opinion. Okay? Well, big deal. There's your raw data. What is the probability now that a person answered that they were for it? This is no conditional, just that they were for it. Well, out of the 100, I see 12 plus 8 plus 5 were for it. So 12 plus 8 is 20 plus 5 more is 25. So 25 out of the 100 were for it. Were for, imagine that, for canceling spring break.
Next.
So we reduce that and we have a 1 out of 4 chance. Okay, so the probability is 1 out of 4 that any person, regardless of their party, was for it. What's the probability that a person was for it given that they were Republican? Now, this is a conditional one. Okay? So we're going to have to do the intersection of both over the probability of B. Well, the intersection of both is that they were for it and were Republican. If you look at your table there, how many people were for it that were also Republican is 8. So your numerator will be 8. Now, that's going to be over the total number of Republicans. And the total number of Republicans, if you look at your table, is 8 plus 25 plus 5. If you add that up quickly, we're going to get 38. Once again, the probability of both happening at the same time is they're for it and they're Republican. Well, there it is right there, 8, over the probability of B, which is the probability that they're Republican, is 8 plus 25 plus 5.
Is that your final answer?
Well, let's reduce it. And there it is, 4/19. Okay, we'll do a couple more. Get you remembering this formula. What's the probability that a person is a Democrat given that they were for it? Okay, well, let's see. Once again, we're going to have to do A intersected with B over the probability of B. So the probability that they are a Democrat and that they're for it. How many people are a Democrat and are for it? I hope you see at the table is 12. Okay, so our numerator will be 12. Now, how many people are just, what's the probability of B, in other words, are just for it? Well, let's look in the for column. And we have 12 plus 8 is 20, plus 5 more is 25. So the denominator will be 25. So we get 12 out of 25. That wasn't so bad, as long as you know the formula. Lastly, what is the probability that a person is a libertarian given that they have no opinion? Well, once again, let's use our formula for conditional probability. The probability of both happening at the same time, their intersection. So the person's a libertarian and they have no opinion. Well, that's easy to read from the table. There's 7 people that are libertarian and have no opinion. So that'll be your numerator. The denominator will be how many people have no opinion. That's B, right? Well, how many people have no opinion total? That's 12 plus 5 plus 7. That's going to be 12 plus 5 plus 7 is 17 plus 7, 24. Okay? So we'll have 7 over 24. It wasn't so bad. Okay? Hopefully from that exercise you'll get the idea of conditional probability and the formula you use.
Oh, this is my very favorite show. I never miss this one.
Okay, totally new stuff. Let's talk about dependent versus independent events. I'll give you a hint. This is going to be related to conditional probability, the difference between these two. Okay?
I demand an explanation.
Okay. Well, consider. Let me give you a situation. If 40 was one of the numbers pulled in yesterday's lottery, okay? Yesterday's. Do you think the probability is better or worse that it will come up today? Do you know? Well, you know what?
Pay attention, son. This is for your own.
What about tomorrow? Is the probability, even if it came up yesterday and today, is the probability better or worse that it'll come up tomorrow? Well, you need to know that those are completely independent events. They have nothing. It could come up all three or not. They have nothing to do with each other. Okay? In plain English, I would say they have nothing to do with each other. Let me give you a different one, if it would. Okay, if I pull a jack from a deck of 52 cards, okay, I just pulled a jack. I only have 51 cards left. Assuming I don't put that card back, is the probability better or worse that the next card will also be a jack? Well, that really affected it, didn't it? Those two events are dependent events because they really affect each other. Well,
This is all very sophisticated.
let's come up with a formal definition of independence. If the probability of A, given that B occurred, is simply the probability of A, and also it has to work the other way too. If the probability and also the probability of B, given that A occurred, is simply the probability of B, then you can see they really have no effect on each other. Then we call them independent. Okay? Basically, if the occurrence of B has no effect on the probability of the occurrence of A, and vice versa, then we define A and B as independent. Now, they're either independent or dependent. So if they're not independent, then we say they are dependent. Now, levels of dependence we'll measure another day, but the idea is, as long as they're not independent, they're somewhat dependent.
Allow me to demonstrate.
Let's do one. Rolling dice, two separate dice, is certainly independent events. If I roll a dice, of course there's 6 possible things that can happen, and I roll another dice, there's 6 possible things that can happen. The probability of getting a 5 on that first green dice is 1 out of 6. We know that. We've done that before. The probability of getting a 5 on the second dice is just 1 out of 6. They're completely independent. Now the probability of A intersected with B is the same as the probability of A times the times the probability of B. We know that from the multiplication principle. The probability of getting 2 5s is going to be the probability of getting a 5 on the first dice, which is 1/6, times the probability of getting on the second dice, because they're completely independent. And it'll only work if they're independent, won't it?
I know that, dude.
It's going to be 1 out of 36. You already knew that. The chance of getting 2 5s is 1 out of 36.
I don't understand.
But drawing cards, of course, if you don't replace them, are dependent events. Remember pulling our 2 jacks? The probability of pulling both jacks, okay, from a deck of 52 cards is not going to be the probability of getting 1 jack times the probability of getting another jack, because we didn't replace it. This time it's going to be the probability of the intersection of A and B, of getting both jacks, is going to equal the probability of getting 1 jack times the probability of getting a second jack, given that you've already drawn a first jack. You can't just, blow off the fact that you've drawn that first jack, because it is related, because the sample space is 1 card smaller now. So the probability of actually drawing 2 jacks is 4 out of 52, right? Times 3 out of 51. The other 3 out of, assuming we picked a card out of our sample space. Considering that we picked a jack first, the number of jacks will be lowered and the number of cards will be lowered. So everything changes. It's not 4 over 52 times 4 over 52, because they are dependent events. I should say they're not independent. Not independent events, so consequently they are dependent events.
Warning, warning, warning.
Now don't be confused between independent events, the ones that their occurrence has no effect on the probability of the occurrence of the other, and something like flipping heads on 2 coins. Now coins have no effect on each other, okay? Don't be confused between that and what we talked about last time, mutually exclusive events. Those are events that can't occur at the same time. Independent events can occur at the same time. Okay, mutually exclusive events can't occur. For instance, flipping heads and tails on the same coin. That's mutually exclusive. It can't occur at the same time. Okay? But flipping heads on 2 coins, I can do that. It doesn't have an effect on each other, but I can do it.
I'll leave you with this final thought.
Okay, well, you know what time it is now. It's time for you to get busy. Let's get going on that homework. It's the best way to learn. Do it.